Hi everyone, first of all, thank you all for joining us today. In this session, we will be presenting a tutorial on explanations in interactive machine learning, and the content will be an overview of the research on how explanations are combined with and facilitate interactive capabilities to build models that result in not only better performance, but also better user experience. So I would like to highlight one thing. There exists quite some works in the area of explainability and interactivity in machine learning, but as we have limited time in this session, we'll be covering some of these works, and we have provided references to the works that we cover in this session at the end of this deck. We have also brought together the links and references to some other important works in this area, also some previous tutorials and talks, and we included them in our tutorial website, and you can see the link of the website at the end of the slide. And this slide deck is also included in the tutorial website as well. So for this tutorial, we have 4 presenters. As you see the names in the slide, we have Stefano Teso from the University of Trento, myself, Öznur Alkan from Optum-United Health Group, Elizabeth Daly from IBM Research Europe, and Wolfgang Stammer from the Technical University Darmstadt. We are all interested in interactivity through explanations research and have some work in this area. Therefore, we are very excited to present this material to you today. All right, so let me give you some overview information about the structure of the tutorial before we actually start the content. We have structured our talk in 4 main parts, and each of the speakers will be presenting one part. Before we start presenting the sections, we will first briefly introduce ourselves, and each section will take more or less 22 minutes, and we'll make sure to leave sufficient amount of time to run a question and answer session at the end of the tutorial. So please note down any of the questions you have during the talks, and we'll be trying to cover them and discuss them with you after all 4 sections are completed. For the outline, in the first section, I'll start with an introduction and motivation to explanations in interactive machine learning. This will basically be a warm-up session for presenting some information around why explanations and interactivity are important and how they facilitate each other to build interactive machines. And I will also briefly touch some fundamental works in this area, some of which will be further detailed in the following sections. And this first section will be followed by 3 in-depth sections, which are divided based on different explanation types, since different explanations facilitate, different interaction mechanisms, as you'll hear more about it later. Stefano will be presenting feedback on attribute and example importance in section 2. And in section 3, Elizabeth will present feedback through rules. And finally, in section 4, Wolfgang will cover interaction through concept-based explanations. All right, with that being said, let's start the first section. And before starting the content of the first section, let me first introduce myself. My name is Öznur Alkan. I'm currently working as a lead AI engineer at Optum, which is part of the United Health Group. My research focus has actually evolved over the years, as may be the case for the others. However, I started my journey with recommendation systems and sequential pattern mining. More recently, my research has focused on designing interactive algorithms for some challenging business problems in AI machine learning space. And actually, more recently, I focused on methods and techniques to infuse user feedback into the machine learning models. And for the context of this first part, I will first start with an introduction and motivation, and then I have chosen 3 key fundamental areas, the works that will prepare you for the following sections. These 3 areas are exploratory debugging, active learning with explanations, and finally, interactive recommender systems. Finally, I will conclude my part with briefly touching some challenges that we have in interacting with the models. All right, so let's start with why we need explainability and interactivity. As we all know, AI and machine learning is everywhere now. They are highly integrated in business, and thanks to the supercomputers and machines we have and advances in AI, we build algorithm solutions that have very high performances, that can parse complex and multimodal data, and that can predict or recommend with very high success rate. However, over the years, as we focus more and more on performance only, this surge in performance leads to increased model complexity, turning such systems into black box approach. Black box models are created directly from the data by an algorithm, meaning that humans, even those who design them, cannot understand directly how variables are being combined to make predictions, or in other words, how variables are jointly related to each other to reach a final decision. However, this very limited knowledge of internals of the machine brings uncertainty to the users in terms of how these systems operate or how they come up with specific decisions. And this sort of an uncertainty has made it problematic for machine learning systems to be adopted in sensitive yet critical domains, such as, for instance, healthcare or criminal justice. Therefore, we need something more. We want to trust the machine, and we want to trust the machine to be able to act upon its predictions. And how do we trust as humans in real life? We want to understand, we want to hear the why, and we want to have some ability to fix problems or errors if we observe any. And this brings us to explainability. Recent years, we have witnessed fantastic advances in explainability in AI research, or XAI. And with XAI, we can interpret models for complex black box models. For instance, we build surrogate models to reveal some understanding or interpretability for the model's decisions. Without explanations, as proved with several studies, users actually struggle to build accurate mental models of these machine learning systems, which make it hard for them to consume the predictions or recommendations. With explanations, on the other hand, users can get an understanding about why. In some explanation types, why not, so that they can compare alternative decisions, and they can more quickly get a catch on and understand when models do fail, which in turn leads to trust. And with XAI, AI models become more consumable for the end users. Explanations, okay, we said explanations are good. We need them in many critical scenarios. However, are they enough? Yes, with machine learning models and the explainability, we can ease decision making. However, the most recent information always resides on the user side. Consider, for instance, the business or domain experts, right? They know a lot about what's going on in real life. They know, for instance, there can be exceptions in life. That in some cases, for instance, they need to act differently than what is expected. And sometimes rules change in business, regulations change, and they need to be able to immediately apply those new rules to their decisions. However, for instance, if we consider model-based machine learning, they depend on what they learned from the historical data. Therefore, it's hard to adapt to new rules that the training data set not yet captures. Therefore, expert knowledge is critical to act accurately when there's a drift in model or drift in data. Even for online learning solutions, expert knowledge is proved to be very valuable to learn quickly how to act in specific configurations and to quickly learn a policy. Therefore, interaction is very valuable for models to make better decisions and to quickly learn and to quickly adapt. Okay, with that being said, think from real life, right? Interactivity or providing feedback is not easy. If you don't know what's going on inside, if as humans, for instance, we are not provided with some context, we cannot imagine how to provide feedback, or we don't know the way we provide feedback or the feedback that we provide, whether it will have an impact on the machine learning model's decisions. And at this point, explanations come as a very natural solution. By observing the machine's explanations, users have the opportunity of building a better understanding of the machine's overall logic. And this not only helps to troubleshoot the model, but also facilitates and amplifies our natural capacity of providing appropriate feedback. So this at the end facilitates the feedback loop. Okay, so the key takeaways are explanations have the benefit of serving as a ground for interactivity, and these two perfectly work together to build human-centered AI solutions. Let me now present you some fundamental works on interactivity through explanations, which also proves these statements through the user studies and experiments they have reported. And I will first start with exploratory debugging, which is a fundamental area and work in this space. In 2010, Kulesa and the other authors proposed this idea of exploratory debugging, where the idea was to build a two-way exchange of explanations between an end user and the machine learning system. The idea emerged from the following question: how can end users debug machines when they make an error? Or how can end users actually influence the models to help them to perform better? And in order to solve this challenge, they present exploratory debugging to allow users to debug or fix the programs via a natural language-based methodology. And to demonstrate this idea, they initially made a formative user study where the test is from the coding domain. They present users in paper some coded spreadsheets where the codes were prepared by an expert, and later on they intentionally introduced errors by randomly changing 30% of the expert's codes. However, the user study participants thought that the codes were actually assigned by a machine. And you see an example in the slide now. There were 4 codes for each transcript, and users were asked to inspect whether the code is correctly assigned by the machine, and if not, why. And they recorded how end users think machine learned programs make decisions. And users were presented codes with explanations and without explanations. They find out that when the codes are not accompanied by explanations, the corrections users make are different. Since users do not know how machine assigns code, they think machine uses presence of words, but not the absence of a word to decide decoding. However, once users learn it, which happens through observing it through the explanations, they provide some corrections, including the absences as well. I think that's a very interesting and motivating finding that shows how explanations actually guide user feedback. And the authors then used these findings in a later on empirical study where they used a naive Bayes model that uses these learned rules. And in the second study, they follow users to mark explanations as incorrect or some features used to decide the codings as incorrect, which were directly added as new training data instances to the model, and they directly update the model with this new data. And experiments demonstrate that F1 score, which is the metric they use to evaluate the naive Bayes classifier, significantly improved after consuming user feedback. Therefore, this work overall shows explanations facilitate and guide interaction types, and interactions at the end improve model performance. So later on in 2015, Kulesa and the co-authors published another work in IUI, which built upon this first one. And in the second one, they described principles of exploratory debugging. So they basically laid out exploratory debugging in a way as a framework, which needs a set of rules and principles to be properly implemented. Okay, let's go over these principles quickly because I believe they are really important in general to consider when we want to provide interactivity through explanations and when we want to provide interactivity in general for a machine learning model. And these principles are centered around two main areas, explainability and correctability. Explainability principles aim to accurately explain the learning system's reasons for each prediction to the end user. This principle builds upon research showing that explanations are a necessary condition to help end users learn how a machine learning system operates. And to help users build useful and accurate mental models of the learning system, the explanations should be sound, they should be complete, but also they should not overwhelm the user. What does that mean? So first, they should be sound, meaning that they should not be simplified too much by explaining the model as if it were less and less complex than it actually is. One method for evaluating the explanation soundness is using the fidelity metric, which evaluates the alignment between the explanation labels and the labels of the machine learning model for a, of course, classification test. In general, with fidelity, you can evaluate the alignment between the model's decisions and the explainer's decisions. With being complete, we need to have a complete explainer, meaning a complete explanation does not actually omit important information about the model. But don't overwhelm refers to the balance between the soundness and the completeness. For instance, a neural network can be explained as if it were a decision tree, but this can reduce soundness because a different model is explained. And similarly, for instance, consider a model with 10,000 features. It can be explained as if it uses only 10 most discriminative features for each prediction. However, this reduces the completeness by omitting information that the model actually uses. Second top-level principle for exploratory debugging is correctability, which somehow aims to allow users to explain corrections back to the learning system. So this somehow investigates the key factors we need to keep in mind when we design user interactions with the machine learning model. We should be able to design explanations that can be acted upon. So in a way, actionable explanations should be in a form that people can leverage their existing knowledge by adjusting the explanation to match their own mental reasoning. The second principle is explanations being reversible. This refers to having a mechanism to undo the possible harmful actions humans can make, which in turn help users to identify and recover from the errors. Third principle and fourth principle were actually related. Third one is always honoring user feedback. This is rooted from an earlier finding that a system that appears to disregard user feedback deters users from continuing to provide feedback. And lastly, incremental changes matter, means some user interactions may not always result in large, obvious changes. So being able to communicate the small incremental changes is critical. As similar to always honoring user feedback, this may prevent otherwise users from, disengaging from the whole process of providing feedback. In their paper, they also built a demonstrator system called ElucidDebug to showcase how these principles can be implemented. And the experiments they made with ElucidDebug were motivating. For the sake of time, I'm not going in details for ElucidDebug, but overall, these were very interesting works for explainability and interactivity in machine learning. All right, now with that being said, we will move to another very important area for user in action type of machine learning models, which is active learning.
Thank you, Öznur. Hi, I am Stefano, and I will present the second part of the tutorial, which is about interactive machine learning with local explanations. I will cover selected interactive approaches based on two different kinds of local explanations: input attributions, also known as saliency maps, and example-based explanations. Unfortunately, other approaches from the literature, especially from natural language processing, had to be omitted because of time constraints. Let us start from methods based on input attributions. I'm sure that you all know what input attributions are. Given a predictor and a target decision, an input attribution identifies what input variables, say words or pixels, are most responsible for that decision. Two important aspects shared by most input attribution techniques are that, on the one hand, they tend to ignore architectural details and are therefore applicable to all sorts of predictors. On the other, that they are only valid locally around the target decision. Approaches differ in how they define responsibility and in how they carry out the computation. Well-known methods like LIME and SHAP are perturbation techniques and work by sampling points around the original input, while input gradients and GradCam look at the model's gradient with respect to the input, and as such, what matters is the sensitivity of the model's output to infinitesimal perturbations. There are also rule-based techniques that we will not touch upon in this part of the tutorial. As Öznur mentioned, machine learning models learn from data are prone to picking up confounds and shortcuts from the data. This can occur, for instance, when the training data is not representative of the data distribution on which the model will be applied. One common scenario is that the training data is too small for the task at hand. This leads to so-called clever hands behavior. What this means is that in order to maximize the accuracy on the training set, the model ends up relying on features that correlate well with the desired outcome in the training data, but that are not causal for it. This compromises test set and out-of-distribution performance. Consider the image to the right. Here, a certain model has picked up a shortcut from the data. All images of horses include a particular watermark text. The model then classifies new images as horse if, and possibly only if, the watermark is present. As shown by this example, input attributions are a great tool for identifying clever hands behavior because they facilitate spotting cases where the model relies on confounds. This is especially important for high-stakes applications like diagnosis of COVID-19 from X-ray images, where confounds may consist of metadata like text snippets or artifacts, as shown in the picture. We have already seen that standard interactive machine learning protocols are opaque. For instance, in active learning, the human in the loop can neither observe nor directly affect the model's beliefs. This makes it very hard to explicitly fix the shortcuts picked up by the model by providing annotations tailored to that end. This, in turn, makes it hard to determine whether the model can be trusted. Explanatory interactive learning opens the black box of active learning. In explanatory interactive learning, the machine repeatedly presents query instances to an annotator, but in addition, it also provides predictions for those images and input attributions for its predictions. In the original implementation, the explanations are computed using LIME. This helps the user to gain an understanding of the machine's reasoning and to assess competence, for instance in cases where explanations highlight clever hands behavior, as in the image to the left. At the same time, explanatory interactive learning enables the user to supply corrective feedback on the machine's explanations. In the example, the image is classified correctly as wolf, but for the wrong reasons, namely because of the snow patch in the background. In this case, the user can tell the machine not to use the snow. This supervision is then used to drive the machine away from clever hands patterns. Compared to previous approaches, like explanatory debugging, explanatory interactive learning is more widely applicable in that it targets modern machine learning models, including deep neural networks, and it does so by leveraging tools from explainable AI. The question is, how does one integrate corrective feedback into the model in a way that is applicable to a wide variety of models? Let us first look at model-agnostic techniques, and specifically to CAIPI. Recall that corrections identify false relevant pixels. CAIPI converts them to counterexamples and adds these to the training set. In the previous example, the correction tells the model that the snow in the background should be irrelevant to the prediction. In order to capture this information, CAIPI synthesizes a small number of examples that are identical to the original, except that the snow pixels have been randomized. The label of all of these so-called counterexamples is the same as that of the original image. The counterexamples are then added to the training set as if they were regular examples. In doing so, the counterexamples teach the model to predict the right label without relying on the randomized pixels. It is important to notice that counterexamples essentially capture invariances. That is, the label stays the same regardless of the value of certain input variables. In this sense, this means that they are the opposite of counterfactual examples. Let us look more in detail at how counterfactual examples affect the learning process in CAIPI. In the image on the left, two hypotheses in red and blue both predict an instance X correctly, but they differ substantially in what features they rely on. Let us assume that the second feature, X2, is actually irrelevant according to the user. As you can see in the second panel, in this case CAIPI draws counterexamples close to the original instance X, where the irrelevant feature X2 is randomized while the label is kept the same. As the third panel shows, this implicitly eliminates one of the two hypotheses, the one that relies on X2. This can be shown to be technically equivalent to introducing an orthogonality constraint that encourages the model's decision surface to have a certain direction and that is valid in the neighborhood of the target example. Another class of approaches aligns the model to the user's corrections in an end-to-end differentiable manner. Consider input gradients. This is a well-known attribution algorithm that associates responsibility to each input variable proportionally to how sensitive the model's output is to small perturbations to that variable, all else being equal. Notice that the input gradient also conveys directional information. Other differentiable attribution techniques tend to generalize the same basic template. This immediately suggests an alternative to counterexamples. The idea is to directly penalize the model for relying on known irrelevant attributes evidenced by input gradients or other gradient-based techniques. This immediately leads to the right for the right reasons loss, or RRR loss, which is high whenever the square of the input gradient of an irrelevant input is away from zero. This loss brings several benefits over CAIPI. For once, since the input gradient of a differentiable model is itself differentiable, the RRR loss is itself differentiable. This enables end-to-end training using this loss. Moreover, this loss is straightforward to implement using standard automatic differentiation packages, like PyTorch or TensorFlow. Another benefit is that it does not require extra space to store the counterexamples, and furthermore it requires no sampling, which can take time to perform and introduces variance into the learning procedure. Here we see what imposing a loss on the input gradient looks like. Ideally, the RRR loss essentially aligns the input gradient of the learned model to the input gradient of the ground truth, if it exists. Since only some of the null entries of the ground truth gradient are known, that is, those associated to the irrelevant input variables, the loss focuses on those. As in CAIPI, this is equivalent to a local orthogonality constraint. There are several alternatives to the RRR loss, some of which are listed in the table to the left. There also exist several variants that depend on how label information is used, shown on the right. Some standout alternatives are grad mask, which has a contrastive flavor, and the right for better reasons loss, which looks at how the input gradient will change upon retraining the model. A curated list of works on this topic is available on GitHub. Several experiments have shown that CAIPI and the RRR loss give users fine-grained control over the learned hypothesis. These approaches were used, for instance, to fix clever Hans behavior in the analysis of scientific data, and specifically in a plant phenotyping experiment, shown on the right. In this case, a CNN had learned to discriminate between healthy and diseased leaves by relying on the light speckles appearing in the watery medium on which the leaf is floating. Using explanatory interactive learning, domain experts managed to quickly teach the model to look on the leaves instead, substantially improving the relevance of their scientific results. Summarizing, both CAIP and explanatory interactive learning and the AAAI laws can help a human in the loop to fix bugs in the model and assess trust. The main differences between these alternatives are that, on the one hand, CAIP is completely model agnostic but has larger space requirements, involves sampling, and relies on possibly unfaithful explanation techniques like LIME. On the other, the AAAI loss requires the model and attribution method to be both differentiable, but it is space efficient, stable, and easy to bring up. It is worth noting that CAIP can be viewed as a sort of inverse LIME, and the AAAI loss as inverse input gradients, and that given the tight relationship between LIME and input gradients, indeed it was recently shown that one approximates the other, then CAIP is also tightly related to the AAAI loss. Another important point is that these strategies do not require the user to provide complete corrections. Even small improvements to the model's explanations are sufficient to improve the model overall. Another interesting approach is interactive attention learning. This approach is similar in spirit to explanatory interactive learning, but it goes beyond it in two directions. First, it targets model with a learnable attention component. The model's attention plays the role of a gradient-based explanation and is used to set up an explanation-based interaction with the user. Second, since the attention component is a smaller model and partially separate from the main network, retraining it based on the user's feedback can be much faster while requiring fewer corrections overall. This can help to reduce the cost of model updates. Another important aspect is that interactive attention learning selects instances and features to be annotated by the user smartly by prioritizing those that are more likely to be incorrect and that once corrected had the largest impact on the model. The ranking of candidate instances and features is done by adapting techniques from query selection in active learning, such as uncertainty sampling and influence functions. We are now ready to discuss FIND. FIND builds on the observation that input attributions present a necessarily partial view of the model's reasoning, making it hard for end users and debuggers to see the larger picture, and that moreover correcting them can have unclear effects on the model in regions far away from the target instance. FIND, which stands for Feature Investigation and Disabling, is an interactive debugging strategy specifically designed for natural language processing models that presents a more complete overall picture of the model by combining relevance information from multiple local explanations. FIND focuses on correcting bad word class associations. For instance, cases where a word with a positive sentiment, let's say lovely, plays the role of a confound and ends up being associated with classes that have a negative polarity, or that are not related with sentiments at all. FIND specifically focuses on realistic NLP models composed of two main elements, shown below. An embedding function mapping inputs, so text, to latent features, for instance a bird-like architecture, and a dense layer at the top mapping latent features to classes. These architectures make it easy to figure out how a latent feature is related to any class, as shown by the middle image. However, they make it very hard to figure out what specifically latent features represent at all. In turn, this means that the relationship between specific words and specific classes is completely black box, thus obscuring potential bugs. FIND works as follows. First, it explains the user what each latent feature means. This is achieved by applying layer-wise relevance propagation, a technique akin to input gradients, to the embedding layer. This gives relevance scores for all input words and all latent features. This information is summarized using a word cloud or our n-gram cloud. The user can then identify bad word class associations by interacting with the word cloud, for instance by indicating cases where the model is using words and by proxy latent features incorrectly. This feedback is then used to force some of the weights of the dense layer at the top to 0, indicating that some features should not be used for certain classes. The dense layer is then fine-tuned under this constraint while keeping the embedding layer fixed. Another group of interactive methods leverage example-based explanations. These explanations illustrate the reasons behind individual decisions by identifying those training examples that are most responsible for them. An obvious strategy to measure the impact of a training example on a model is to remove it from the training set and check what happens upon retraining. This is, however, often too slow. Perhaps the most well-known strategy for identifying relevant training examples are influence functions, a technique from robust statistics that was recently shown to also work reasonably well for non-convex models like neural networks. The key advantage of influence functions is that they do not require retraining, and moreover, they admit a useful form of caching, making them viable for human-in-the-loop applications and larger datasets. By default, influence functions enable evaluating the impact of a training example on the model's parameters. Another advantage of IFs is that, thanks to the chain rule, they also allow evaluating the impact on the class scores, on the loss, and on other smooth functions of the parameters. One debugging technique that makes use of influence functions is healed IF. The idea behind this approach is that the model's predictions may rely on the wrong examples, which entails that it associates them to large an influence. In order to fix this, healed IF enables the user to supply supervision that is used to, indirectly, correct the influence of the examples on the model. Healed IF is designed specifically for natural language inference tasks, but the same ideas applies to other domains. Healed IF repeats the following steps. First, a set of examples from the validation set are chosen as anchors. For each anchor, healed IF selects the most negatively influential training examples, that is, those examples that if upweighted will decrease the loss more, and shows them to the user. The latter then assigns a score in the range of 1 to 5 to the similarity of each anchor point to the influential example. Low score implies that the anchor is being wrongly influenced by the training point. In order to correct for this, healed IF augments the dataset by synthesizing random copies of the training point using synonyms and back translation. The number of copies is proportional to the similarity indicated by the user. This ensures that more similar points, those that should have higher influence, indeed achieve higher influence. The last approach that we will cover is Sensor. This method is designed for sequential learning settings, which are ubiquitous in human-in-the-loop applications like crowdsourcing and citizen science. In these applications, annotators may be inexperienced or unwilling to report, and as a consequence, the labels may be noisy. For instance, in the right image, the user provides a bad label to the machine, thus affecting the model's performance. One way to cope with this is to double-check and relabel those incoming examples that have low likelihood according to the model, that is, those examples for which the machine is skeptical. We say that a machine is skeptical for the right reasons when there is a clean training example, similar to the incoming one, that supports the machine's skepticism. For instance, the user might have been at a party before. The machine can look up this training point and use it to uncover the user's white lie. But if the machine is skeptical because of a noisy training example that it has received in the past, then we say that it is skeptical for the wrong reasons. In the figure, for instance, the machine is skeptical because of the user's past white lie. The idea behind Sincert is to explain the user why the machine is skeptical by identifying those examples that most support the machine skepticism and allowing the user to relabel them if necessary. In the top row, the machine is skeptical for the right reasons. From left to right, first, the machine receives an example incompatible with its decision surface, which is clean. Next, it presents the user the one example that most supports its skepticism. In this case, it is blue. Finally, the user recognizes that the counterexample is correct and agrees with the machine. In the bottom row, the machine is skeptical for the wrong reasons. First, the example provided by the user on the left is labeled correctly, but it happens to fall in a region of the decision surface that has been corrupted by a mislabeled red example. Next, Sincert identifies this noisy training example based on its influence and presents it to the user. Finally, the user notices that the training example is indeed mislabeled and relabeled it. The machine is then updated accordingly. The overall process enables users to get rid of noise in the training data and in turn facilitates learning better and more trustable models. Let us summarize the main points. Human annotators naturally supply explanatory feedback, which is useful for correcting the bugs in the model. We focus on human-in-the-loop strategies for modern machine learning models and based on modern XAI techniques, and specifically input and example-based attributions. We stress that the key intuition, that of presenting explanations and learning from corrections, carries over to tasks beyond computing. Up next, Elizabeth will tell you more about interacting using global explanations.
Okay, thanks so much, Stefano. So my name is Elizabeth Daly, and I'm a research scientist at IBM Research in Dublin. And I started working in this area in particular when we started needing to be able to deploy these kind of machine learning models in business scenarios. And sometimes the end user is not going to be a data scientist or a machine learning expert, it's going to be someone with business knowledge. So the things we're going to look at, one is why are rule-based explanations something that are useful and something for us to look at. We're just going to touch upon how you go about learning rules and rule-based explanations, and then how can we leverage these rules to facilitate a user-in-the-loop and interactive machine learning. So what we've looked at so far is local explanations. So local explanations are really useful to enable the user to build a mental model of individual predictions, but it's not easy for the user to explore all the different instances, and their real knowledge of the underlying model's behavior is going to be heavily influenced based on the instances they've been able to explore, and how are they going to get a clear model, a mental model of what's going on if they haven't been able to explore the different instances sufficiently. In reality, this can be heavily biased by what samples are then shown to the user. So they might think they understand what's going on, but if they were to look at all of the instances, they might discover areas where the model is not performing as they would like. So what we're going to look at here is global explanations and rules used as global explanations, which allow the user get a bird's eye view of what is going on in the machine learning model. And it avoids this narrative bias that might occur when looking at local explanations, but this simplification may come at a cost. Obviously, if you're going to summarize complex behavior, it could be that you are sacrificing some of the accuracy. So there are a couple of strategies when you're going from trying to generate global explanations. One is that you might try and get a bunch of local explanations and generalize them. The other scenario is that you might try and do some kind of model distillation, where you try and get a single model that encompasses the behavior of a more complex model. So why are rule-based explanations something worth thinking about when we think about interactive machine learning? If we think about the slide that Öznur showed at the beginning on what we want to facilitate from interactive and machine learning, being able to answer those key questions. So I understand why. So I understand why the prediction is being made. If you look at a rule, we understand these things. So we understand what features are being used to make the prediction, and we understand whether we agree with those that logic that's being applied. We also can then look at why a prediction is not being made, and be able to understand what features are missing or what parts of the rule are not being fired appropriately. We know when you succeed, so you might be able to look at your data and say how many data instances actually support the rule that we're applying. But we also can look at where we fail. So we can look at data instances that do not agree with that rule. We can take a look at those data instances and we can see, do we agree with the fact that they don't apply? Does it mean we need to tweak that rule? Does it mean we need to create a new rule to cover those instances? And we can use that information to better tweak the rule-based model in order to reflect our objectives and our belief of how the decision criteria should be being made. And you can have, because the users can understand a rule, hopefully, we can get the user to have their expertise and intuition to be able to say, yes, this rule looks good, or no, this rule looks bad. And so we're really trying to take advantage of the fact that the rules are something that are interpretable and something that a user can examine and look at, and let them use their common sense or their domain knowledge to be able to validate or invalidate some of the rules that are found. So just to touch upon learning the rules. So there are two different ways that we are going to look at or discuss briefly on how rules can be learned. So one is that you can learn it directly from data. So you try and get rules that are going to fit based on the labels that are coming from your underlying raw data, or you might want to train a complex machine learning model of some sort and then fit the rules to cover the labels that your machine learning model has given. And so in this way, the rules become a surrogate to try and reflect the decision-making process that your machine learning model has learned. So there are many different algorithms, and I'm not going to go into detail on all of them here, but these are ones that people can dig into if they're interested on how you can do rule induction from data and from either from data sets or or from machine learning models. And these algorithms differ in a couple of different avenues, in how they go about doing the rule generation, but also in terms of how they manage some of the different trade-offs and things like rule complexity, how long the rules are, how many rules are given in order to try and reflect the decision-making criteria, the accuracy, and also things like whether they're going to try and maximize for non-overlapping rules. So are they going to take into account that rules can overlap with each other, or are they going to try and minimize this? The other differences on how you're going to present the rules. So are you going to present them as a list or as a set? Are there going to be a sequence of if and else's clauses? And so the different algorithms take somewhat different approaches. Here, let's just assume that we have a mechanism for generating rules and that this is something that we're going to be able to allow the user to interact with to influence in some shape or form. The reality is that in order to become more accurate and really accurately reflect the decision boundaries, it could be that the rules might have to become more and more complex in order to cover narrower slices of the data, which might end up negatively impacting interpretability. So I mentioned some of the solutions are learning the rule-based models directly from data, but some are trying to use model distillation. And so there you have a predictive model, you have the data that's used to train the predictive model, and then you use that model to provide the labels, and you use that to build an explainer, which is a simpler and interpretable model, which is trying to mimic the model's predictions. So in this case, the outcome could be a set of rules. There is other work also that looks at things like decision trees, but for the purposes of this tutorial, we're going to keep focusing on rules. So now I want to cover a couple of different ways that we've seen that people are leveraging these rules in order to facilitate interactive machine learning. So it could be that you use the rules to become the model in itself. So it could be you either take the data or you take a machine learning model and create a rule-based surrogate, and you actually let that become the rule-based model that you will execute to make your decisions. In this case, obviously the decision-making criteria is transparent to the user because the rules are the model. Or there's work where the user takes this as the starting point and then edits the rules. Or we can use it as a guide in order to help elicit user feedback and annotations. Or it could be used to give feedback where the model is influenced by the changes to the rules. Or we can use it to try and uncover differences in between different machine learning models. So one of the first pieces that I'm going to mention here is a paper that focused on assuming that rules are built from data. And then you have a web-based editor, and that web-based editor allows the user to edit an existing rule. So a rule might have been learned from data, and the user can change things associated with that rule. They can add certain rules, they can remove rules. So you might think about some domain knowledge or external expertise that they want to have encoded in the rule-based model, or they allow you re-rank some of the rules by editing things like their confidence. So editing which order in which the different rules are going to be able to fire. So the advantages are that the rules are transparent to the user is able to see them, and they're able to edit them and change them based on business needs, based on domain expertise and so on. And it provides full transparency. Also, it has the advantage that we're not expecting the user to come with all the rules of the knowledge system that they're going to deploy. We use the data to guide with an initial starting point for the rules, and then the user can tweak and edit those. The disadvantages are that the rules must govern all features and decision-making criteria. So if you're going to use those rules to make all of your predictions, and you have many different columns that are potentially feeding into the final decision and the final prediction, you're going to need to have all of those features encoded in the rules, and you're going to have to be able to have the user understand those different features and how they should relate to each other. So this might affect interpretability from the end user perspective. Then we have work that Stefano was involved in terms of how we use it for guiding active learning. And so there we have that rules are used to be presented to the user, and they can look at these rules and particularly try and examine rules that have a low confidence value associated with the data. And then you present the rule to the user, the instances that the rule covers, and the label according to that rule. So the idea is that the user is able to quickly look through those instances and see if they agree with the rule, the label that's being provided by the user, or by the rule, excuse me. And so the user can correct those instances, and with those corrected instances, they're fed back into the model, and the model is retrained. And this can be done in an iterative fashion. And so the user it could be used as a more effective mechanism for eliciting labels and feedback from the user than randomly selecting or even just using uncertainty-based active learning approaches. One of the real advantages here is that because the rules are just being used to guide the user feedback, they do not need to include all decision-making criteria and all features that are relevant for a prediction. They just need to be an appropriate enough summary to guide the user and get them to triage some of the instances. Then there's recent work that myself and Öznur were involved in, along with some of our other colleagues. And this is where we were using a rule-based explainer to be able to present rules that apply to specific instances and show those rules to a user. And so let's say they did not agree with the decision-making criteria being applied, they were able to correct this information. So assume we had the rule that I had earlier where someone was being denied a loan on the basis of the fact that they had a PhD instead of a master's. So you present this information to the user and they can correct it and say, well, actually, I would have accepted this person on the basis of that. So we then store this feedback back into what we refer to as the feedback rules lookup table. And we develop a transformation function that takes the input instance and uses a somewhat counterfactual based approach to be able to say, well, if it had conformed with the rule that the machine learning model knows, would you have accepted it? So for example, if we see that a PhD can be substituted for a master's, if that person had been flagged as having a master's, would you have accepted and marked it as approved? And if so, you can return that updated prediction to the end user. So the user can correct that rule. And those transformation functions are being stored to be able to test whether the feedback from the user would have changed the prediction or flipped the prediction associated with it. One of the advantages here is that it supports user adjustments without having to retrain the model. In our case, when looking at this kind of work, sometimes you have the ability to be able to influence the machine learning model, and other times it could be that it's deployed in a business scenario where you do not have the ability to retrain the model. Or it could be that you don't have the ability to have access to the training data. And so for this reason, we developed this solution where you could apply somewhat of a patch or band-aid to an existing machine learning model. Again, the rules do not need to reflect all of the features. It needs to just reflect the features that the users are going to be giving feedback on and that they can understand. One of the disadvantages is that it assumes that the rule is genuinely reflective of the underlying decision boundary, because we're using that decision boundary to generate these transformation functions. And what we found from experimentation is that the results do deteriorate if the user feedback diverges too much from the underlying machine learning model. And so there's only so much that can be done if you've only got partial information, and the underlying machine learning model's knowledge diverges too much from the feedback from the user. And this is something that we found very useful where certain business policies might have changed, where let's say a threshold might have been introduced or adjusted from a machine learning model perspective. And because the rules are something that a business user might be able to understand, we found that they were able to more readily understand what the impact of those changes should be on future predictions. So then follow-on work with Öznur and myself was FROAT, which is feedback rule-driven oversampling for editing models. And this is inspired by work from the popular SMOTE algorithm to be able to deal with class imbalance problems. So here, instead of reinforcing existing decision boundaries, here we're using sampling and synthetic data to be able to move decision boundaries. So again, in the example I gave previously, where let's say a threshold might have changed, we take that as an external feedback rule, and we also have access to the initial training data set and to the algorithm that's been used to train the model that we're trying to modify. And we iteratively can delete or relabel certain data points. And we also then synthesize data points in order to reinforce the feedback rule that's being given by the external user. And so here, you don't need to have rules that reflect the entire decision-making model. You just need the rules that are reflective of what the user is trying to encode in the data. And so it could be that you, again, have some kind of external policy that you're trying to get reflected in your underlying machine learning model. And the optimization methodology tries to make sure it minimizes the impact to the performance and prediction accuracy over the segments of the data that are not reflected or impacted by the feedback rule. So the advantage here is that you're encoding the feedback rule into the underlying machine learning model, and it supports expertise that's differing from the historical data. So you are able to encode something that might not have been reflected in your training data. And then one of the pieces there, when we went about trying to modify these underlying machine learning models, we wanted to be able to understand, has the machine learning model truly learned the feedback rule that's been given from the user? And so it also brings us to another use case for rule-based surrogates and rule-based explanations, is how can you use those rules to let a user understand how two machine learning models differ beyond accuracy? How do their decision-making criteria differ from each other? And so to do this, we leverage existing work on generating rules from data called an algorithm called BRCG. And you first use that to train a rule-based surrogate that's reflective of the initial model. then you use those rules as grounding and input into another run to be able to compare it with a different model, model B. And the rule generation process optimizes for accuracy and compactness of rules, but it also optimizes for semantic and statistical similarity between the given rules. So it tries to make sure the clauses are as similar as possible and that it represents the same data points as much as possible, so that it's possible to be able to compare the different rules and see what might have changed between the two machine learning models. And here you see two machine learning models trained on the same data. One is a linear SVM and the other one is an RBF SVM. And you can see that on the lower right hand side, the rules show that there are actually quite different decision logic encoded in these two different machine learning models, even though it's meant to be reflective of the same data. And then finally, we have a piece that was a demo in NeurIPS, which tries to bring these pieces together, where it builds a rule-based surrogate from the input data, which you can then export and use the rules themselves as the executable model, or you can modify them using the machine the feedback rule approach to be able to modify the underlying machine learning model and then export the data that was responsible for generating that machine learning model, and also compare the different models to be able to verify that the expertise or the feedback rule that you've tried to encode truly has been encoded into the underlying machine learning model without negatively impacting the other clauses that were reflected in your model. So the advantages and why we believe that rules are an interesting mechanism that people might want to explore a bit more when it comes to facilitating interactive machine learning. So it helps supporting users forming a mental model of an AI system, and it presents a logical mode for user feedback. So we all understand rules, we understand how they should work when we're trying to evaluate them. And so trying to make adjustments and understand what the impact of that change should be is something that is useful. You can imagine if you're trying to change the importance values of tabular data and saying this feature should be more important than another, it's hard to predict what the knock-on effect is going to be for certain follow-on predictions. Whereas here, you're encoding what you expect to have happen for follow-on predictions. It also aligns well with business logic. So one of the things that really drew us to this is when we were trying to get machine learning algorithms and models to be deployed in a business setting. And sometimes the historical data did not align with what were the current business rules. And so being able to encode business logic was something that became important. And we've also shown that it allows you to gain insights into model differences that are beyond accuracy. What are the different decision-making criteria that are encoded in different models that may have very similar accuracy metrics and are also trained on the same data? What are some of the challenges? It really is most suited for binary classification for most of the examples that we've looked at. The reality is that you can have conflicting rules. So if someone's going to modify one of the rules, you need to do some kind of post-analysis to understand what are the rules that need to be updated that might be now conflicting with the information there. And also the rule induction algorithms typically are restricted to input features. So you're not necessarily going to get complex features or derived features here. And so with that, we've discussed rule-based explanations, and I'm going to pass it over to Wolfgang to discuss concept-based explanations.
Okay. So can everyone see my screen?
Yep.
And you can hear me. Okay, excellent. All right. So yes, hello everyone, also from my side. I am Wolfgang Stammer. I'm a PhD student in Christian Kersting's lab in the Technical University of Darmstadt. And as already previously stated, I'll be focusing in this section on interacting via concept-based explanations. So let's just dive in if it works. So previously we focused on sort of interacting via local and global explanations, where we mainly focused on input attribution-based and rule-based explanations. And as Stefano and Elizabeth had already discussed or pointed out, these approaches have huge benefits, but they do also have some limitations, which I will discuss in the next few slides. And in this section, the idea is to look more at specific model types and how the explanations of these model types can have benefits for explainability altogether, but also in terms of interactions. And we'll be focusing here on concept-based models and neurosymbolic models, which are related specifically in terms of the benefits of sort of a higher level, higher semantic level of a model's explanations. So looking at sort of particularly input attribution-based explanations, there are works that show that there's a specific limitation of these, which is actually that there's a lack of precision in these explanations. So it's just sort of visualized here on the right, where a CNN predicts a colored 0 or a colored image of a 0 as a digit 9. And if you look at the explanation, it doesn't really give you much, because the explanation looks correct. It's on the right input regions of the image. And what this example actually visualizes is that there are specific sort of concept relationships in an image which cannot be visualized in the input dimensions themselves. And so these sort of input-based explanations have this issue of sort of understandability, but then also if you don't understand it correctly, you can't revise it correctly. So it would be very sort of advantageous for a human user or a user in practice to also access sort of the more internal concept representations of a model. But of course, this is particularly difficult for black box models. And so one idea, one suggestion is often to use more white box models, which by design, of course, allow for more introspection of the whole decision process of a model. So examples of these are, for example, shallow decision trees or sparse linear models. And these are kind of related to many of the approaches discussed in the previous section by Elizabeth. There are some issues, though, with these models, namely that they often require categorical or otherwise symbolic input data. They therefore struggle with more like sub-symbolic data, and therefore also don't generally support representation learning. So the question is, what other alternatives are there? And so, like I mentioned, we'll be discussing sort of two kind of model types that to some degree reduce these limitations of the previous approaches. And I'll start with the concept-based models. So what are concept-based models? This is a concept-based model is sort of a general term of models that encompasses sort of partial selective interpretability. So for describing like the whole decision process of a model, it sort of divides this up into two decision processes, or two steps in a sense, where you often have a bottom level module and a top level module, where the idea of the bottom level module, which is typically actually a neural module in the end, is to extract from the original raw input samples sort of higher level concept activations. And then the goal of the top level module is actually to, given these sort of concept activations, also concept vectors, to produce the final final prediction. And in this sense, there are two sort of distinctive properties of such concept-based models, which is namely the final decision of the model is somewhat independent of the original input, given the concept activations. And additionally, the whole idea is that these concepts representations are human aligned. So this idea of interpretability, or sort of partial interpretability, comes from this idea that parts of the model are human aligned, whereas other parts are not. So there's several works by now on sort of concept-based models. They all differ based on the sort of the type of representation of the concepts. And I will briefly just go over a few sort of core ideas. So the most intuitive one is obviously that the sort of this concept extraction is supervisedly trained. So human users give, for example, via one-hot or multi-label one-hot encodings up front, give the supervision on the concept space. Where interestingly, Ko et al. In 2020, they in their paper, they also provided evidence that given like a proper or a sufficient set of concepts, such concept-based models are on par with completely black box trained neural networks. Another idea, which is more from a sort of an unsupervised setting, is where an autoencoder structure learns sort of a set of basic concepts together with relevance activations for these concepts. And these are then aggregated in a sort of top level module. So these concepts are then learned more unsupervisedly, but the advantage is that due to the sort of encoder decoder structure, a human user can introspect the concepts, making it more understandable so you can visualize the concepts and see what in fact these concepts represent. By now, actually, quite a number of works has focused particularly on prototype representations within these concept-based models, where the idea is that a particular image or like parts of an image within the encoding space is compared to a particular prototype representation, like prototype vector. And the similarity between the encoding of the image and the prototype encoding is then used as this sort of final activation, which is then passed on to sort of the concept aggregation step. Another sort of final idea I want to highlight here is that, and also in fact, the sort of this concept learning can be learned interactively. So in the work by Lage and Doshi-Bellis in 2020, a model proposes specific associations between input level features and concepts, and then a human user can interactively sort of vary on whether the associations are correct or not. So the idea of, or sort of the basic assumption of these concept-based models, that specific like discrete or symbolic concept level representations are advantageous, particularly for interpretability, can also be found in neurosymbolic models. Although it's important to mention that sort of the research branch of neurosymbolic models was not developed mainly for the purpose of interpretability. So in general, the idea of neurosymbolic models is to combine the benefits of the neural subsymbolic computations and symbolic representations, where the idea is that this has advantages for generalizability and overall predictive performance. So here's an example from Yi et al. Where a near-symbolic approach is presented for visual question answering. And what you can also see here is that the structure is often similar to compared to concept-based models, and that often like a neural module is used to process the sort of raw input data to more specific sort of representational space, which then in terms of near-symbolic models, a symbolic module, for example, often like a logic-based module, is used to actually process this, other input representation. But so several recent works have actually also now begun to investigate the benefits of near-symbolic models, not just for the overall predictive performance, but also, or specifically in terms of interpretability and also then revisability. So how would one actually like interact now with such explanations? Let me start with the sort of interacting with concept-based models. So not surprisingly, of course, concept-based models can also be faulty or prone to like confounding factors. So it's like, of course, desirable to also interact with these or to maybe even revise these. Now, the special issue with concept-based models is, of course, due to these like separate modules, you have sort of different ways of interacting with these modules. And recently, Bontempelli et al., for this reason, they presented a sort of unifying framework for debugging concept-based models. And particularly for this purpose, they propose a sort of multi-step process where the idea is that given a sample X and then a predicted label and its corresponding explanation, which is not high quality in the sense that it's not as desirable as a human user would want. One first essentially goes about on identifying, so from these sort of two modules, what is actually the source of the sort of the false behavior. And then, so this can be either in the concept extraction from the bottom level module or in the concept aggregation from the top level module. And once the source has been identified, then of course, one should go about the specific sort of interaction protocols for that model or that module. So I'll just give you I'll show you some examples on recent works which have investigated the sort of the different parts or these different levels of interactions. So this is the work already previously mentioned. I'll just say a bit more. So in this work by Lage and Doshi-Veles, again, the idea is from sort of high dimensional tabular data that a model proposes specific feature concept pairings or associations to a human user, and then the human user either corrects or otherwise accepts sort of these associations. So in this sense, so from so for example, for medical data, an association for the concept anxiety might be sort of the feature from the input data of generalized anxiety, whereas insomnia might not be directly linked to the concept of anxiety. Another idea, which recently I had also worked on, was to use the sort of the advantages of prototype representations for discretizing the encoding space of a model and grounding this sort of encoding space based on these prototype representations into like a semantically concept-based space. So the advantage then is once you have like the sort of semantically grounded discretized space, a human user can very easily interact with the model. And then, for example, provide the model feedback that in fact, like several objects do not share the same concept, but should be divided up into like two concepts. Now, moving on to like interacting with the top level module, also some recent work also by Stefano, Teso, the authors applied a sort of ranking loss between user feedback of the concept relevances and the predicted concept relevances from self-explainable neural networks. And this is sort of also reminiscent or quite similar to the like previously seen XIL approaches, but on this sort of concept aggregation step of concept-based models. In another recent work, Bahadori and Heckerman, they actually added an interesting aspect of causal learning into the loop, namely stating, so if a confounder exists in the data, this will probably not just influence the input data itself, but also then these concept vectors. And so they propose a sort of two-stage regression technique to prevent this or to debias then such models, where the idea is to first debias the concept vectors using the labels Y, predict the debiased concept vectors using the features, and then finally use the predicted concept vectors in a second step to predict the labels. Another very interesting idea comes from Ko et al. In 2020, where they introduced this idea of sort of test time interventions on concept vectors. So a human user can now interact by manually updating specific concept activations that a model has predicted in order to improve the model, so to get a correct prediction. But in this sense, the user can, of course, also use this sort of causal intervention idea to just investigate the model itself. So why does it predict specific classes given like these and these concept activations? So moving on to sort of interacting with more neurosymbolic models, I'll be focusing on just a few works. Of course, there are more. In this work by Sarah Wegner et al., the idea was to integrate deep learning with human-driven first-order logic explanations, where they propose a sort of a neurosymbolic model with a deep neural network that maps the input space, in this case with images, to a concept space. And then a second logic module uses the concept space from the neural network to build a sort of rule-based explanations and use these explanations for predictions. Now, the cool thing about this, particularly using this logic-based representation of explanations, is that a human user can now easily add sort of prior knowledge into the loop by adding constraints on these logic explanations, for example, like the length of the explanation or other kinds of logical constraints. Now, in this work that I was also, took part in, the authors propose a sort of object-centric concept learner, a near-symbolic concept learner, where also here an image is mapped first into like the tabular or the structured concept representation, and then a second module makes a prediction based on this concept representation. Now, the cool thing about this is that you can receive neuro-symbolic explanations, which correspond to which image regions were important for prediction, similar to what we've seen before. But now the human user can also receive from the model more symbolic or semantic-based explanations. And now the cool thing is that the human user can interact with the symbolic explanations, where the authors did this by integrating a sort of right for the right reason loss, which we had already seen previously, on this sort of neural reasoning module. And this feedback that the human users can give can be in relational logic form. So this has the advantage that now the feedback can be on local and global levels, in the sense that a human user can say, okay, for this image, don't focus on this concept, but actually for all images of this class, don't focus on this concept, or for all images altogether. And in this way, then a model can be trained with a human in the loop on the sort of right object-centric semantic reasons. A sort of brief recap, or not recap, but overview of like further domains, because many of the previous works we discussed focused mainly on sort of classical image classification tasks. This idea of the benefits of sort of simple ground explanations also has sparked or also has research in other domains. Particularly, this idea comes quite natural in sort of the planning setting, where many of the approaches already work on sort of discrete representations from the start. But there's also some recent work in the sort of reinforcement learning domain, where, so for example, in the work of Bonnet et al., a human user can give feedback to proposed state action pairs by a reinforcement learning agent in sort of two ways. One in like a binary feedback of saying, yes, this is good or bad, so reward penalty, but also in the form of sort of explanatory object-centric image regions, or marking object-centric image regions which are important or not important for the decision. Another interesting approach was from Za et al., where reinforcement learning agents learn from human demonstrations, and to improve this setting, the authors build into the model that the model should ground what it sees in these demonstrations in terms of human-aligned symbols. And with this, the model sort of self-explains what it sees, and it can improve the overall performance. So coming to the end of my section now, so sort of the overall message is that human-aligned concept level symbols as a way of like just overall prediction, but particularly explanation and interaction has huge benefits. Importantly, this does allow for a sort of more natural level of communication and explanations altogether, somewhat more reminiscent of how human-to-human explanations and communication goes. So the models that we briefly like showed in this section, so the concept-based models and the symbolic models, by keeping sort of neural aspects as well as symbolic aspects, they somewhat overgo some of the limitations that the previous interaction approaches were missing. Just a brief summary. So here we presented sort of that there are various possibilities within these models of how to represent the actual concept representations. And so based on this, there are also different possibilities of the explanations themselves, of presenting explanations, as well as how to interact. And a brief mention here, so there's an excellent Blue Skies paper, also at this AAAI conference by Kampampati et al., yeah, that presents a good overview actually on this topic. So there are some remaining challenges, particularly for these sort of concept level explanations, and like the largest criticism is, of course, how to like obtain such human aligned concepts, as in many cases it might not actually be completely clear. We've seen some approaches which you know, go in this direction, but this is still a major challenge, I suppose, particularly because it calls more for like an online fashion that it's possible to suggest like a certain set of concepts and notice that they're not sufficient enough. And so this sort of concept representations, it would be good if they are revisable. So that's all to my section. And that sort of concludes in the main part. I'll just give a very brief overview of the main takeaway. So if, I mean, tutorials always have a lot of information, quite a packed amount of time. So if there's one message, I guess, to take away from this tutorial is the following: that explanations are a vital part in understanding the internal reasoning of an agent. However, it seems that, or we argue that, explanations can help to go beyond the sort of one-way communication as a mechanism to actually elicit user control. And so in this tutorial, we presented several approaches and research focusing specifically on combining explanations with interactive capabilities. And we've seen different approaches here, which mainly focused, and so we distincted here between sort of the level and the overall approach of the explanation. So we focus here on sort of more input, attribution-based, concept-based, and rule-based explanations. And we hope that you've seen, like from this tutorial, that overall explanations make sense in all kinds of active learning protocols. But yeah, so several exciting challenges and avenues, of course, still exist within this field. And we hope maybe this has also sparked your interest for future research. And with that, I guess, so thank you very much for listening. And I guess we're open for questions. Now I just need to stop the recording, I believe.